I would love to give the floor to Sarah Johnson to talk to us about gravity in Swift.
That's the beginning as well. Okay, hello everyone. I am from here in Durham, but actually just down the hill at the Institute for Computational Cosmology, and I'm very excited to be talking to you today a bit about what I'm doing in my PhD, which is all about doing GPU offloading for gravity within the Swift code. I'm going to walk you through all of them. I also want to apologise because I've somehow managed to acquire a cold in June, which is the most British summertime thing ever. So if I'm a bit snuffly or a bit coughing, please forgive me for that too. So I realise many people here may be from an astronomy background, but for those of you who maybe aren't, this might be the kind of thing you're used to thinking about when you think about astronomy. Nice picture of the universe. Pretty than this, because my version of the universe looks a lot more like this, because I focus on building the universe within simulations. So I specifically look at the formation of large-scale structure within the universe. And when we study that, we call it really cosmology as the overarching field. So the whole point of formation and the development of the universe over time from the Big Bang to the present day, using supposedly maths and physics alone. But the thing is, when you have this much science to consider, we really have to start thinking about large amounts of compute. You know, we want to study every structure from something that is the size of the universe right down to the size of what for astronomers is small, an individual galaxy, not small for the rest of us. And we need very large and very memory intensive simulations to make this kind of thing happen. And that is where we start to join up with HPC. So HPC systems for years now have allowed astronomers to run these large-scale simulations. But HPC itself is also an evolving field, and we've seen trends in the new systems moving towards having larger numbers of GPUs, for various reasons: performance, sustainability, cost, etc. But this gives us a bit of a divide here between what the astronomers want from our systems and the kind of systems that we're actually being given to work on. So if you have never encountered a GPU before, this is a graphics processing unit. And these are multi-core accelerators that allow us to carry out multiple calculations at one time. And the kind of trade-off here is a GPU's cores are a bit less powerful than a CPU core is, but we get more calculations to kind of balance this out. GPUs, I love them. Here's a nice picture of me. This is my favorite GPU. It's in Cosmo, which is just down the hill. It's a Grace Hopper. I love it. I've broken it so many times. I'm really sorry about that.
Yeah.
Okay. Can I be heard online now if I'm just talking through my own microphone? Yay! Amazing. A nice pause in the program. I'll now resume. And hopefully everyone online can still see my slides. So, cool. So, your quick recap before the break, GPU offloads and gravity. So the method actually for this is not very complicated. It's not revolutionary. We take the existing Swift code, which is written in C. We write some GPU kernels to replace some of our gravity functions in CUDA. CUDA is the NVIDIA vendor language for GPUs. There are various languages available. I feel like it's always good to preface that like a little sales disclaimer. I chose CUDA because it was the easiest one when I was starting out, but I'll come on to talk a bit about portability a bit later in the talk. And then once we have these kernels, we call them in place of the CPU functions in the code and link them all together in a makefile with a couple of partially compiled files and all the relevant libraries and churn out Swift GPU. And this took a little bit of time to get up and running, but it has, for the past couple of years now, actually been a functional thing. So Swift GPU has been around for a while. It's just not necessarily always been very performative for that time. But one of the things that is really important when it comes to the science side of things is, does it work? Like, it's great if computationally it works, but does it actually scientifically work? So one of the sets of pipeline tests that we devised is, this is a power spectrum. So this shows basically matter clustering on different scales. So the scale is the bit that goes along the x-axis, and basically the amount of clustering goes up and down the y-axis. Now, the top plot you can basically just ignore, and the bit that we really care about is this bottom bit down here, which is the residual or the error section. So that grey margin marks 1% errors, and you can see the black line that shows the error difference between the CPU and GPU lies within that, basically up until the red dashed vertical line, which represents the Nyquist frequency, which is where our simulation size resolution starts to kick in. So we've managed to have very high accuracy results in terms of matching the GPU with the CPU. So the GPU has been able to do exactly what the CPU has been doing, which is fantastic for our science. If you are more of a visual person, this is the plot I like to show for visual people, which is just to say that we managed to create structures that are important to us. So this is the cosmic web here shown for CPU and GPU. I always like to say spot the difference between these two, and then some smart aleck always goes, oh, well, one's blue and one's pink. But what I mean to say is if you look at the kind of structures that we're producing in both of them, you'll see that we are producing the same structure. So our gravity is working on GPU, which is really important to us. But the problem for us initially was there wasn't enough work for the GPU. We were giving it a very small amount of work. The GPU is an incredibly highly optimized device. It can do a lot of calculations. And actually the overhead on our memory transfer way outweighed the amount of calculation we had to do. And so we didn't have any code that was performative and optimal in any way. So we came up with a solution, which was this idea to try and send more than one cell at once together to the GPU, which is an interesting problem to try and fit into Swift's task-based kind of architecture here. So we developed this thing called task bundling. In task bundling, you take one of the tasks in Swift, and rather than do what you normally do, which would just be to send that off to the GPU on its own and then take it back and update the values, is we actually take a load of them and we pack all the data for the cells that are in those tasks into long contiguous arrays. Partially because this helps with our data transfer to have everything uniform kind of together contiguously put in, but also because it gives us lots and lots of data to transfer and then lots of data to do calculations on. And once we send that to the GPU, we edit the kernel so that it performs the same operations, but looping over different subsections of the data to represent the different cells that are going to be needed to be updated. It fills in a results array and then transfers that back. And then when we get it back onto the CPU, we unpack all of those results back into their relevant cells again by storing information about the addresses of the cells we want to update. And this means that in this illustration, I've put 8 tasks, but in theory, you can bundle together thousands and thousands of tasks that we need across the run to make sure that we are getting enough work for the GPU to be performing well. However, in a task-dependent system like Swift, you need to be really careful with the dependencies because all of our tasks can then go on and unlock other tasks that can do more work. And if you say do something like don't update the accelerations before you move the simulation on a step, you'll find that the universe looks less Big Bang and more completely still and strange blob. And that's not what we want to have either. So we installed a system that made sure that we can deal with the tasks appropriately by ensuring that all the dependencies get locked as soon as we access and bundle a task. And then the work can be done on that task without ever unlocking the dependencies. And only when it returns to the CPU with all of its work complete can we check and unlock the dependencies and allow it to spawn further tasks. And this is like a change to the existing Swift tasking system by essentially holding some tasks on pause until the GPU is ready to do its work, has completed its work and transferred back, versus the usual Swift system, which is as soon as a calculation is done, something is unlocked and the next thing can be triggered. The other thing to say is that we aren't necessarily going to get the perfect number of tasks to pack. So it may be that we have a pack size that we've chosen, but not the right number of tasks to fully fill that up. So we also need to consider how we're going to flush our system every so often to make sure that we're actually getting all the work done. And one thing that I found really interesting is looking at how we can use GPUs in a way to actually do better science as well as just better computational performance. So within Swift, there's a few different types of gravity that come through. And essentially, if you look at this diagram from top to bottom, this is in increasing amounts of approximation, so decreasing accuracy as you go down it, and increasing length scales. So particle is our very small local length scale, and multiple is the one that's working over very large distances. And originally at the start of my PhD, the idea was just take the particle, that's the simple one, that's the one that's easy to spread, put it on the GPU. But as I was developing more and more, I was suddenly realizing, why don't we get some more work by doing other types of gravity in a slightly different way? So we've scrapped the particle multipole approximation and we've changed that to direct particle. So we're actually getting more accurate results now from the GPU as well, while also giving it more work to do, which is keeping the GPU occupancy high and making sure our memory transfers are being balanced. And I'm really proud of this because I think getting better science out of better technology is a really great outcome to have too. So in case you want the kind of plots of the accuracy stuff, higher accuracies towards the left of these plots, and you can see that if we look at residuals and our errors on accelerations, that our GPU is always giving us smaller errors. So we're getting closer to ideal values by using this GPU full particle case, as we call it. The other thing is there's lots of GPUs out there and we want to use as many of them as possible. So although I write in CUDA, which is the NVIDIA language, we want to be able to use AMD GPUs too. So we have a portability abstraction layer in there that can convert between CUDA and HIP at compile time, and you just put in command line arguments to compile with the correct libraries. There's also a bunch of automatic sizing commands to make sure that you don't overflow your GPU. It bans the user from doing stupid stuff, which I was told is very important, because the top thing I've been told by system managers is users are silly, and to stop them being silly. So this code, you can put it onto any NVIDIA or AMD GPU and it will automatically size itself if you give it the wrong size so that you don't break your GPUs, which I think is fantastic. But here's the bit people actually care about. And I want to say this is the first time that I've ever got to show a speed up result in a talk. It's been 4 years and it is really worth it, I've got to say. So I want to say, if you're a computer scientist, these speed ups will not look that exciting to you, but they're very exciting to me. So this is a test case of what we call our Eagle boxes, which are these simulations that kind of evolve from early times through to cosmic web style structures, with these different amounts of particles that you can see here. And this is an example using my favorite GPU, the Grace Swapper. And this is comparing actually to that approximated CPU version. So this is already a more ideal CPU case, and we're still managing to outperform it. And our performance is also getting a lot better the larger our problem size is as well. So we're able to tackle larger problems at higher accuracies in better times, which just feels like a really, really nice thing to say. But if you want a comparison to the actual same science, because bear in mind this is without approximations, we can get speeds up of kind of up to 4.5 times faster for some of our kind of problems. And you can see here a whole host of different GPUs I've been testing on. And there's lots of different things that I could say about this plot. The main thing I'm going to say is there's a lot to investigate here about how we can optimize to different architectures, to different vendors, how we can actually get better performance across the bar, because you'll see there's really varying performance here. So this is something that I'm actively looking into just now. And then the final thing I'll just say quickly is I'm also looking at how we can scale this to multi-GPU systems. So obviously one GPU is great, but most of our large clusters use lots and lots of GPUs. And you can see here, I just have a little baby example. We're only up to 4 GPUs so far, but I'm getting there. Things are slowly getting through the queues on machines to test. But again, there's some work to be done here in terms of strong scaling capabilities and making sure we're actually getting the most out of our GPUs. But as it stands just now, it's very exciting to be able to say that we do have a bit of a speed up and a bit more accurate science. So thank you very much for listening and bearing with the tech issues, and I'll happily answer any questions.
Let's quickly repeat the question into the mic.
Yes, of course. Dr. IPAC, or do you?
What would your ideal be?
Loads of memory, loads and loads of memory. No, from what I found in a lot of my kind of scoping style stuff, I've actually found that the super chip style GPUs, where they have the CPU and GPU on one chip, have performed way better than any other device. So I think something like that. I think something I'm realizing a lot is that the interconnects are incredibly important, obviously, between the CPUs and the GPUs. And I would suspect, although I haven't managed to test it fully, GPU to GPU and these multi-card chips as well. So a really large memory kind of interconnected chip, I think, would be my absolute dream scenario for this. I think it fits our problem incredibly well, and it naturally adapts and scales pretty well as well. But I think for cosmology, memory will always be something that we can fill because we can always give it a larger problem size. But something that has really good interconnect seems to be especially crucially important when it comes to this kind of consideration of the packing and unpacking and transfer times too. Yeah.
Just a quick question. When you said you're going up to 2, 3, 4 GPUs, is that per node or is that just?
That is one GPU to one CPU, but scaling across the system. I also have runs in just now to test multiple GPUs per node. It's just essentially what I can get my hands on at the minute. So I have some stuff that's been tested on Cosma, some stuff that's waiting to run through Tursa, and some stuff that I'm hoping I can do on maybe some slightly different systems to get a few different ideas of the scaling, because I'd like to test strong scaling and weak scaling for different configurations of the code. I think that'll be quite telling about what kind of bits of it need to be optimized a bit more. Kyle, sorry, you're all in a row now.
It's very exciting to see how curious whether it looks like the GPU is getting better. Is that because the CPU performance is getting worse, bigger problems, or is it actually?
Is that this scaling plot, or is what? Yeah, so this is because the CPUs get worse the larger the problem size, partially because When they get to the kind of larger problem sizes, the memory access is not as coherent, I think, on the CPUs, but also when you start to get it across multiple nodes, you then have to have all the MPI communications. And one of the really great things about the GPU that I didn't have much time to talk about, that I was hoping Abuzed was going to talk about, but now he's not here, so you can come and ask me over coffee, is about the system that we have where we reuse the cells that have been packed onto the GPU. So for one pack, you actually get way more usage of the data than you do in the CPU version, essentially. So you don't have to do as many back and forth accesses with it.
Maybe we have time for one more question while Will sets up.
Yeah. Yeah. This is
You know this.
this is not mixed precision. I have been told a lot to look into mixed precision in various levels. One of the problems with gravity that I've been having is mixing the precision really kills a lot of the detail in the gravity calculations. Although I'm very keen to talk to people who work in mixed precision to find out more about what I could do to stop that being such a big issue.
Okay, I think that's okay. All right, great. Yeah, so I'm. Is it okay? You're saying. Right, so I'm going to tell you a little bit about projects that we've been working on for the last 10 years. And it's to build sort of a next generation cosmological simulation code. So sorry for the jumpy thing, it looks much better on my screen. Okay, so just to sort of set the stage for you. What we want to do is simulate the universe on a computer, okay? So why? Why do we want to do that? For a number of different reasons. Probably the biggest reason is to be able to do numerical experiments, okay? Something you can't do on the real universe, but you can decide what physics to turn on and off in a simulation. You can also, ultimately the goal of our whole idea is that we're physicists. We want to understand the physics that goes into forming the galaxy population the way it is. And so the nice thing is, I think we now mostly agree on what the physics is, which I'll talk about in just a minute. And finally, of course, we want to interpret observations. So we have all these, billion-pound, dollar, whatever facilities that are online, and each one of them does some particular bands and looks at some particular snapshot at a time. How do we stitch all that together into a full 3D movie of what the universe has been doing since the Big Bang until today, right? So that's the goal of these things. Now, where are we? So there's a large number of people who are doing these simulation projects. So this is just a little panel that shows a subset of people who are doing these types of simulations. And when I say a cosmological simulation, what I'm talking about is box size that are hundreds of megaparsecs in volume, typically the biggest ones today with up order a kiloparsec spatial resolution. Each particle represents or cell represents something like 1 million suns, and there's millions of galaxies, hundreds of thousands, millions of galaxies. So that's really good. You get a great statistical sample, not quite the high resolution that you'll hear about from some of the Zoom stuff that we'll talk about, but you can really compare to all these big surveys. So what's the physics that goes into that? Obviously, gravity. We just heard about that. Everybody kind of agrees on how that should work, at least, in terms of what the equations are. We have cooling. Everybody sort of can get roughly the same answer. We have something to do with the interstellar medium and associated star formation. I would say that everyone kind of can get a decent answer for that, but there's still like a lot of questions as to how to do it well. And then there's the stuff that's really uncertain. However, I would say that nobody has been able to make a cosmological model that didn't exclude all of these things that actually worked and made galaxies, right? So you need all of those, right? But exactly what this means and how this is implemented varies a lot. And that's the big difference between most of these models, right? And then there's other things that people are starting to think about, like magnetic fields, maybe important, probably not so important. Radiation fields, not important generally, but if you look at the very early universe, definitely very important. You hear about that from Jen. Cosmic rays, which everybody says is important, but no one has any idea how to implement. Okay. So that's kind of the situation right now. And we're trying to figure out, what are some of the ways we can test these models. Okay, so I just want to show this movie to illustrate that there can be big differences. So this is from the Camels project. And what that project is to run literally hundreds of thousands of simulations. They're all kind of the same simulation, but they're run with many different codes. Okay, so this just shows the same simulation. I'm going to show a MOOC here. Same simulation box with 8 different codes. And this is just the temperature maps in these codes. Starting a very high redshift, early universe, we start to go and we start to see essentially supernova feedback starting to heat the gas. You see in this Ramses thing. Here's Simba. This is our group simulation. You see that, oh, this is really a crappy streaming, but anyway, you can see these sort of big jets and big outflows. Obsidian is the one that's kind of related to ours. And what I want to emphasize to you is that all of these simulations produce pretty much the exact same galaxy population. Okay? And so by the time you get down to low redshift, these things show very, very large differences in a lot of properties, even though they're producing roughly the same galaxy population. So the question is, you know, this is why we still do all these simulations, right? Because clearly this is not the same as this, right? And so, and yet, all of that physics, you know, and it's because of the way the physics is implemented. Okay, so let's talk a little bit about Simba. I won't go into too much of a history, but essentially Simba is our group simulation we've been working on. You know, it was first put out in 2019, has a bunch of stuff. And it's, although it's not the most highest dynamic range, it has a lot of interesting physics that has led to a huge number of spin-offs. The point I wanted to make out of this is that, you know, something like Simba, not even one of the biggest simulation groups out there, but this has already had like hundreds of papers produced with these simulation models and all its various galaxy formation sort of spin-offs or fan fiction, as I like to call it. And essentially, you know, what this means is that you can use these simulations for a huge number of different purposes, right? And that's why we do these. So, you know, you have to create these big simulations in order to do that. Okay, so what, now getting a little bit more technical, what is in our next generation of simulations that we've been working on since Simba came out over the last sort of 4 or 5 years? So we've heard about Swift already. We've heard why Swift is great. So we're using Swift. I'll talk a little bit about the new hydrodynamic scheme that we have in there. Also with the new ISM subgrid model, which is based a lot of stuff on work we did with Britain. Star formation, won't talk about that too much, or chemistry. I'll talk a little bit about the star formation wind launching, which is another sort of very novel aspect in Kiara, and the wind propagation with the so-called fire hose model. I won't talk too much about this, but again, we have a new, but pretty much everything has been touched from Simba, right? So essentially, we have a new code called Kiara that you know, essentially is a big step forward in terms of the input physics. Okay, so let's look at some of these things and just, you know, illustrate why it is we want to we're putting so much work into these kinds of things. So Magma 2 is a new SPH methodology. SPH is, of course, smooth particle hydrodynamics, so it's a very nice way of solving the Navier-Stokes equations in an adaptive frame with no grid, right? So that allows you spatial and temporal adaptivity for free, essentially. SPH has had a lot of problems. One of the big problems with SPH is that all the kernels are assumed to be spherical, which means that there's a lot of sort of, you know, blobs of things interpenetrating with each other. There's a lot of problems with surface effects, so on and so forth. So Magma 2, I think, is the reason we put so much effort into it is I really think it's a significant step forward in SPH, and it makes it almost not quite as good as grid codes, but you know, much less expensive to run than a grid code, right? One is the change is artificial viscosity. Won't get into that. That's a little bit detailed, but the big difference, I think, is in these kernel gradients. So in SPH, essentially, you're computing a given particle's properties by some sort of a kernel smooth average over its local neighborhoods. Okay, fine. Everybody else had done this as sort of with radially symmetric kernels. Right? With Magma 2, you don't have radially symmetric kernels. Effectively, you have a correction matrix that takes your radially symmetric kernel and turns it into a tensor. Okay, so now it's a 3x3 tensor which essentially is determined based on the spatial distribution of its neighbors. Okay, so now basically you're building in information about the local neighborhood and the gradients in there. That's the big advantage. It has a lot of nice features. This is a spherical blast wave. Won't go into too much detail, but it's a problem that's very difficult for SPH. Just wanted to show a couple of other examples. On the right side here, you see a Kelvin-Helmholtz test. Okay, this is just stream moving, basically waves in water, right? And it's supposed to do that. Most SPH codes do not do that. And the reason they do not do that is because the SPH kernel requires a lot of artificial viscosity that essentially smooths out these waves, right? Or it creates the opposite, is you create a lot of surface tension, and that also sort of damps out these waves. And so this SPH code actually does that, pretty much as well as a lot of grid. This is another test that's absolutely amazing for an SPH code. I've never seen an SPH code do this. This is really simple. You start a box of gas, with two different phases, but in pressure equilibrium. The principle is just stated, right? It's in pressure equilibrium. Right? Does it? No other SPH code does that. After a while, basically after a few sound crossing times, it'll turn into a spherical blob because SPH is spherical. Magma 2 doesn't. This is many sounding crossing times. It's still complete square, right? So these are the kinds of things that Magma 2 does well. Does it make a difference for galaxy properties? I don't know, but probably not the dominant thing. On the other hand, we're getting to a point where we should care about small details, right? And these are the kind of small details that could be important. So here's an example of the kind of improvements, the kind of things we think about for the input physics. So this is the subgrid interstellar medium model. Okay. So in simulations, we want to form stars, we want to form black holes, etc. The problem is, as I mentioned earlier in the talk, each one of our particles represents 1,000,000 times the mass of the sun. So obviously, we're not going to form single one solar mass stars, right? We're going to have to treat things in aggregate. Nonetheless, what we would like to do is follow processes that we know happen on the interstellar medium on scales of one solar mass, or at least, a molecular cloud scales, something like hundreds or thousands of solar mass. So in the old code, like in Simba, which is already one of the more advanced codes at the time, we have essentially a pressurized one-phase interstellar medium. Each medium is sort of a smooth density particle at a given temperature. That temperature is pressurized to avoid artificial fragmentation. We had all kinds of things. We had an H2 model, create molecular gas, because molecular gas is what drives star formation. We had dust in there, right? We were one of the first to do that. That was all in there, but none of those things are talking to each other. Every single thing was basically tied back to the pressurized one phase. Now, in PR, which is basically based on Simba EOR, which is something that Britain student Ewan Jones and we developed, everything is sort of done much more self-consistently. So essentially, we know that dust catalyzes on H2, right? So we have hydrogen. We can track the reaction rates that turn it into H2 directly. We turn that gas into H2. We can do all this because we have a subgrid cold phase, right? So we have a subgrid cold phase within the particle in some pressure equilibrium with a warm phase. That cold phase can then form H2. That H2 then catalyzes dust. That dust can then feed back into the cooling because dust impacts the cooling rates. That creates a dust temperature solver. So now we can predict dust temperatures. And once we get the H2 can be allowed to directly form into stars, which creates an interstellar radiation field, which dissociates the dust. So it's like this huge loop, right, of stuff that all has to be solved every time step during the simulation, right? So it's much more expensive, but it's very cool. The problem was that was extremely slow. So in the original version of Grapple, Britain is busy speeding that up. I think you'll hear about that this afternoon. But in the meantime, I set out and over a few months turned the entire thing of Grapple into a C version. and also just completely redesigned the code because it just wasn't going to work the way it was structured. And still using the same API, but essentially got it a lot faster. So this is prior to this, and you see Grackle is just dominating the code time. Okay, so this is basically code time taken as a function of number of steps, this fraction of code time. So that's Grackle, the C version, which I call Grackle, down, right? Much better. Now it's all. The other thing to point out on this plot is this is the old SPH used in many other things like Flamingo and stuff like that. This is Magma. Okay, so Magma 2 does take a lot longer, right? It's basically because of you're manipulating tensors and inverting matrices every single hydro calculation. So this would be great on a GPU, right? That would be amazing. I won't go too much into detail, but this was just another problem we had when doing stuff. So this is a totally new way of doing galactic outflows, which we know how they interact with the surrounding medium. But the point I want to make is that basically we basically have to interact these particles in a separate way than letting standard hydrodynamics do it. And we call this decoupling, but effectively before people had just turned off hydrodynamics, but now we're actually computing a bunch of equations that do the surface mixing on sort of an outflowing stream of gas compared to the ambient medium. They would call this the fire hose model, instead of a fancy word. The point is, doing this in Swift was a huge problem. Okay, so to get that to work, essentially to be able to turn off things for a while, let them interact in some separate way, that was a massive undertaking, but we did get it to work, so it all works now, right? So Kiara works, okay, it runs. This is just example. This is called a Vidal plot. For those of you unfamiliar, star formation rate density versus redshift. The points are the data. We get something that looks fairly reasonable. If you want a little more detail, here's some mass functions in various quantities. Again, I won't explain this in too much detail, except to say that the points are the data, or the shaded regions of the data, and generally the simulations are pretty close, right? They're not bad. So there's still some tweaking to be done, but overall, it's now a working code. I want to spend the last -1 minute on essentially the other part of this, which is that once you have a simulation, you just have a box full of particles. What do you do with that? You need to analyze it. This itself is a huge undertaking, especially when you start to get massive simulations, right? So we had a really nice code called Caesar. We still have it. It's publicly available, which takes in a Halo catalog, which you can run, either during the simulation or afterwards. Runs all kinds of fancy things to find galaxies and pre-computes, literally not just hundreds, actually thousands of properties, galaxy photometry, everything, right? So this has been hugely beneficial to get students, quickly up to speed, make quick plots. It makes life so much easier. The problem is it wasn't MPI parallel, and it was pretty slow in memory cognitive, right? And this, despite the fact that I, Python parallelized it and everything. So instead, one of my students decided to take up the project in his copious spare time an undergrad student, to write a ground-up rewrite of Caesar. And thanks to him actually understanding Python, unlike me, he was able to essentially speed it up by an order of magnitude, and particularly to reduce the peak memory usage. But not only that, make it MPI scalable, right? So now we're sort of unlimited in the box size that we can analyze. So add support to halo finders, import merger trees, do all kinds of things, handle sub-halos. The alpha version of this is working. We can run. We can get sort of Caesar-like catalogs out of it. The end user will not know any difference between an Octavian catalog and a Caesar catalog, but it will have been computed in an order of magnitude less time, right? And over the summer, we're going to be basically finishing this up and releasing a beta version, which we hope to apply not only to Kiara, but also to any other simulation, Flamingo, whatever's publicly available, TNG. It should all run through this. Okay, so I think I'm out of time, so I'll just stop here. Still a little bit of work to do on Kiara, calibrating everything, but generally, I think we're getting close.
People have time for one or two virtual questions.
Sorry, this is coming from a complete outsider, but I find it fascinating when you show that plot and different projects compute the same thing and get very different answers. Is it because they simulate slightly different physics, or is it because they use different approximations for the same equations, or is it something completely else?
Yeah, it's basically because, you know, all of these question marks that I wrote up here, we're solving the same physics, but we're doing it in very, very different ways. And so the actual equations that are being solved, mimicking those processes, are not the same. That's basically the problem. And we don't know which one is right. That's the problem.
Mentioned in NAGMA and SPAs that you didn't know how important it would be for simulations. Have you had a chance to test it directly?
Yeah, so that's a great thing about Swift is, you know, you change one compile time flag and you're back to Phoenix or some other thing, right? So that we will do. It does make a difference, for sure. The way we do feedback, particularly from the black holes, is particularly sensitive to having you know, accurate high Mach number flows, interactions, etc. So that makes it particularly. That's why I spent a lot of time on it, because I didn't think Phoenix was going to be up to it, frankly.
Okay, last question.
Said that Kiara is now much more predictable than the way that all the bodies are. Is that reasonable scalability of from the beginning that data layout and everything's working on distributed systems?
Yeah, I mean, so all of that stuff is happening within each particle, right? So it's not a question. We don't have a problem with that. It's just the big problem happens because now, as you see, you have to iterate the convergence for each particle. Well, you know, it turns out that dense gas, you know, in a big galaxy is the worst possible thing. You have a whole bunch of particles that needs to iterate the convergence. And so we have load balancing issues. You know, we have a lot of more dead time than a lot of other Swift codes because we just run into a situation where one piece of the simulation happens to have a big galaxy or a group of big galaxies. Unfortunately, big galaxies also like to cluster together. So that makes it doubly painful.
I'm not sure that's a you problem. I think that no one is mentioning that this happens to everyone.
Yeah, no, this happens to everyone, but it happens less if I don't use this model.
So Swift and all the physics that goes into it. So I can talk very little about physics and focus on the methods that have driven me mad for about 4 years now. And these are Zoom simulations. So I did drop in a what is Swift slide into here, which I'm now just going to show you some pretty pictures and talk about so that you can sort of soak them in. But the important thing that Sarah already mentioned is Swift works across massive scales from like entire chunks of most of the observable universe down to individual galaxies, and even there's a planetary side of things too on the really, really small scale. And this creates an issue because if you want to simulate the largest structures, a really large chunk of the universe, then you naturally have to degrade your resolution to fit in. And if you want to simulate like really high resolution physics of individual galaxies, you need to shrink your volume because you don't have enough space in your computer to fit the calculation. And that's what this plot on the left-hand side of the slide shows here. There's this band of, this is a collection, it is not complete, of simulations run to date. And you get this band of the calculation where everything sort of has to either sacrifice the volume or sacrifice the resolution. But ideally what we want to do is go to the top right where there's this question mark on the plot. And one way of doing this, and the way that I've hitched my cart to over the last few years, is to do Zoom simulations. So you take a large volume like Flamingo, which is full of the large-scale structure of the universe. You find an area of that box that particularly interests you, and you zoom in, and you degrade the resolution in most of the volume, but focus all of your compute in the area you care about. Thus, in theory, making a nice, simple, efficient calculation that lets you reach the stuff in the top right-hand corner of this plot, but without paying the cost. Now, this has worked. This isn't a unique thing to Swift. People have done this with other codes for years now. But it poses a distinct issue for the way Swift was written from the ground up. And that's because Swift is both a particle code and an AMR code at the same time. So the calculation is done with particles. We interact particles to solve gravity, hydrodynamics, all that jazz. But the actual calculation is structured on an adaptive cell tree where you have top level cells of a particular resolution, and then we divide those cells into octrees based on the amount of particles that are there. And if you sort a zoom set of ICs, so where you concentrate all these particles in one area of the box, you get nonsense that looks like this, where you have, in this very extreme case, a gigaparsec volume with a sort of very, it's basically a few dark matter halos in the center that we care about. And you've got this contrasting calculation of 10 to the 8 from the most expensive cell to the least expensive cell. And if you try and run this with normal Swift, you spend 70% of your time doing absolutely nothing, because there is one thread that got the expensive cell and had the bad luck of doing that job for most of the time. So it's just not going to work. I mean, it does technically run, but it's very wasteful. And then 4 years ago, when I set out to do this, the very simple solution was already slightly implemented, which was just put more cells in. So you take the area that you care about and you add a second level set of top level cells there that better resolve the volume. Hey presto, problem solved. You've seen the problem and implemented the solution straight away. But I'm 4 years down and this hasn't yet been released, so that should give you a hint that it's not quite that simple. And it isn't, spoilers. But yeah, so the way we approach doing this from just like a technical standpoint is you take your top level cells, you dump your particles into one of those cells, and you call that a background cell. So this is a low resolution cell that should do nothing in your simulation, and then you do this octree construction, so you get all your subcells within that cell containing the zoom region, and you let the user say, I want my zoom region to be this deep in the tree. And then when you've done that, you can actually identify the cells you shouldn't care about above the zoom region, and then the actual zoom cells, which as far as the code should care, are just another set of top level cells. It's as if you're running just a bog standard uniform box that happens to be that size and is nested in another one. And if you just simply do that, and about approximately 2 years of bug solving and edge issues I won't talk about, you get a code that performs considerably better. So it does vary, but originally it was about 70% better than running master. So the zoom version of the code is to the right on this plot, so down and to the right is better. So it worked. But it's not, again, we're quite early in talk, so there is a lot more to talk about. But the sort of early victory came, and I was very happy. But the next thing I had to do was check that not only have I made it faster, I've made it more correct, or as correct, sorry, which was a fun little adventure when I was presented with this plot, where I don't know if anyone else in the room's like me, but I saw this and went, oh yeah, they're similar. And I just didn't really think about it more, and I celebrated, and then I went back 5 minutes later and I went, hang on a minute. They're not quite the same. This is insane. And there's a tail out to very, very high errors on the gravity calculation. What's going on here? And it turns out it wasn't my fault. It's actually that part of the code was not fully implemented for this test. And if you do go back and implement that, everything is fine. And in fact, the Zoom code is more accurate than the box standard code. And that's just because you're resolving the box better naturally. So that was a fun little adventure into other people's code being involved, not just my own. Right. So everything is faster. The code works. It is correct, which is always the concern. So then I set about optimizing to high heaven. So this needs to run. The whole point of the Zoom is that you're not wasting time. So I need to find everything that is slow and stamp it out. And in the process of doing that, I have optimized Swift in general and shot myself in the foot repeatedly in the process by making the Zoom code perform less well over the standard version of the code. So the first one of these things I'm going to talk about is similarly, it's similar to what Sarah was talking about with the different types of gravity, but mine go left to right, not top to bottom. But basically the distance scales are going left to right on this slide, and you've got the particle interactions, very expensive, done on short scales. The multiple interactions in the middle, which is like this mid-scale gravity interactions, and the particle mesh, which is really, if you want to make your code as cheap as possible, where you want to be doing as much of the gravity as possible, but it will then be really inaccurate. So there's a balance you play between these three different types of gravity calculation. And when we're constructing this in Swift, we consider all the possible pairs in the top level cell grid that could possibly have interactions. That doesn't just include one cell, that can one layer of cells. It can be out to whatever number the geometry requires. And then we work out from our mesh resolution how far we can actually just throw away these pairs to begin with, just because they will be handled by the particle mesh interaction. We then take these cells and these cell tasks at the top level, and we split them through the tree. So you can go down to this level and consider what pairs you can do at this level, etc., 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 until you get to the bottom and you've actually found some cells that you don't need to do because they can be done in the multiple interactions. However, it turns out that the code, because it had sort of FMM gravity blinkers on when it was being written, only ever considered the mesh for that top level, and then was like, oh, it's fine. The pair tasks below that level, there'll just be no op if they can use the mesh, it'll all be okay. But if you go in and actually look at what would happen if you did consider the mesh as you split these tasks down through the op tree, you find that there's actually 90% of pair tasks that are ever created by the code in any situation, not just the zoom, don't need to be done because they are no op. They just go into the task system and go, oh, I didn't need to do anything, and immediately exit. And if you just purely remove these tasks that did nothing, you remove a huge memory weight from the code. You shrink a huge number of the task loops in the rest of the code as well, where you have to loop over how many tasks there are. And you get about 25% minimum speed up just to any Swift run that you're ever going to run, which is exacerbated and the speed up gets much bigger the deeper your tree. If you have a zoom simulation, your tree is very deep. So I've basically taken the biggest shotgun I can get and shot myself in the foot to make my entire 3 years worth of work disappear in one PR. However, it is very good. Everything's much faster now, and we're all very happy. The other thing which I've discovered, which I promised Mark I would talk about, is I was given a set of Zoom ICs with a very, very deep tree in the center, and I ran them, and I discovered actually a lot of the time is spent in what function we call space rebuild, which builds the space and constructs these cells. And 80% of that time is spent in space split, which is the function that does this alt tree construction. And all this is because it's terribly parallelized, because you have one cell that really wants to split really deep. And we have a truly beautifully implemented depth first search construction method for the trees, which is brilliant in most circumstances, except this one, where it's absolute trash. So I went away and went, okay, depth first. Well, there's breadth first. Let's have a look at that, and maybe that'll work a bit better. And it turns out that you can go in and implement this. Is this where I plot? Yes. And just look at doing, I actually ended up, for complicated reasons, doing a hybrid depth first, breadth first thing, because there's clever caching that goes on in the depth first, which when not done, it's a whole thing you can ask me about. But the long story short is, in this particular use case, the breadth first is much, much faster, because you can actually just go down in frontiers and split as you go and parallelize everything wonderfully in the zoom region. It's all very happy. And you get, it's not as big as the 25% before, but you get another 5% increase. The sort of shot in the foot again here is this also affects if you use the non-zoom code, and it is very, very good in those standards. So again, it's very, very helpful, but more broadly. But it isn't a golden bullet, because if you run just like this is a normal equal simulation, so it's just a standard periodic volume. I appreciate that you can't read the lines here. I will tell you that the bottom line is the normal version of the code, which is faster than the breadth first version of the code that I have run, so it doesn't always work. Yeah. So the one thing that makes my work worthwhile in all of this is there is one thing you cannot avoid in Zoom. So if you were to run a Zoom simulation with the normal code, and that's when you're running with MPI, you need to partition the space. That is done at the top level. If you didn't have any version of this extra grid, you would just end up with all of your Zoom calculations being on one rank and a horribly imbalanced mess. So I'm not completely useless. I have put in all this work for a reason. and that is the partitioning. So very quickly in Swift, we construct a graph based where cells are nodes and interactions between cells are edges. And we then, after constructing that, pass that off to Metis and let Metis do all of the complicated partitioning of that graph to give us the sort of optimal partition for the input graph. And we then partition based on that graph and we get down to sort of 5% imbalances between ranks and we stay there, and that can go all the way up to sort of having 500 ranks or more, and it sits there quite happily, and we'll repartition if it needs to, but it's pretty stable. The trouble we have in the Zoom case is we have the Zoom cells inside another grid, so we have to account for all the interactions, so things get a little bit messy, but effectively it actually turns out you can just construct another graph, give it to Metis with these extra edges for the background cells, and Metis quite happily splits this up and gives you a good partition. It just so happens that sometimes it chucks the background onto lots of nodes, and then you have to hand not lots of nodes, onto like one node because that it thinks that's the most optimal split, and you have to babysit it a bit in that way. And if I run this, it can, in this incredibly unbalanced scenario of having all your work in one place, actually get to the 5% imbalance. It's nowhere near as stable as it would be. This is like the best case scenario that I run. It on average is more like 30%, but that's actually comparable to sort of the big flagship runs like Colibri with Swift. And it's still great in the grand scheme of what's come before. There is one wrinkle which I'm working on at the moment, is that the boundary where you have these, I hate presenting through, there we go, for the unresponsive. But yeah, so the boundary you have here around the Zoom regions, the background cells, adds a whole ton of communications because you tend to need to know lots of the small high resolution cells information for the background cell on the outside. So you end up with lots of comms at the boundaries, which get really, really expensive. And there's work currently underway basically to improve this. It's all to do with the fact that the MPI standard will not allow you to post non-blocking sends and receives on multiple threads, which seems like it should work, but they just refuse. Yeah. And now to stop Mladen from losing any more hair, I'm going to skip over that and get to my summary. So yeah, just to summarize, it works. The distributed Zoom runs now work, which was the sort of headache that I've been having for years. I keep shooting myself in the foot, which I mean, for everyone else, is a great thing. It's terrible for my career, though. And yeah, papers are coming soon. I swear to those in this room that have seen this talk several times over the years, they are coming. I have a new job. They have to come out. Thank you. Really not enough physics this time. Oh. Relative to if you did the whole box at that resolution, it would be sort of the same. You'd end up having that time step hierarchy. It's the same between the runs. You just basically cut out a smaller area where the time step hierarchy is horrible and do a smaller calculation, which does mean that you then end up maybe a little bit more inefficient, but with the smaller steps that are happening, because there's just less to do. There's less stuff on those small time steps. But on the whole, the not doing stuff you don't care about balances that out quite extremely. No, it's very, oh, no. So we've got variable time stepping. So yeah, so only the particles that need that small time step are on that small time step. Yeah. So the MPI is effectively dictated by the Zoom meeting stuff. I cut it out of this talk. I normally talk about how we do baryonic physics, which is actually just, as far as the code cares, only the Zoom region has baryons, or it has hydrodynamics and sort of star formation, etc. So the code doesn't really care. It just sees a non-periodic small area that needs to do that stuff, and it's fine. And that's what dictates a lot of the cost and the time step hierarchy for the MPI. Right. I mean, it's been possible for years. So. Okay. But yeah, I mean, I'll be very thankful if they implement.
Shown a couple of
lots of understand things useful.
Mm.
So I would be interested in seeing how much each component of the Zoom code uses. We have something like that?
Yeah, so it's just not talk easily digestible. I can show you. I have a whole Swift Sim CLI with its own logo and everything that needs to go on PyPy, but it has a whole analysis suite for all of this. Uses tree sitter to pass the source code and construct things. It's wonderful.
Okay, so I was trying to prepare this talk and trying to figure out what the audience would be like, and was a bit lost. So this is maybe a little bit scattered, but let's give it a go. So, all right, I want to start with, this is a talk basically about what happens after all these simulations that we've heard about all day are done. You've now got data on disk and you want to do analysis. And it turns out that optimizing the data storage and access to the data is actually also a hard problem, right? Usually the data are stored in the way that is fastest to get them off of the HPC cluster while the simulation is running. That's dumped to disk, and then we have to live with whatever came out on the analysis side, which is maybe not optimal. I'll unpack a little bit of that in this talk. And as always in astrophysics, right, so kind of the fundamental problems here are we're dealing with enormous dynamic ranges. And in particular, this comes down to differences in sort of use cases for the data, because as we've heard throughout the day, right, these data sets are very versatile. There's many science questions you might try and answer with them. And answering those different questions comes with very different data access patterns. And ideally, we want to be able to optimally interact with the data for all those different use cases. But when how the data are stored comes into play, that starts to become more difficult, right? And so, realistic use cases for these kinds of simulations, we're dealing with anything between 1/10 millionth of the data might be an interesting subset to pull out and look at, all the way to, I just want all of it, give me the whole thing. So I'll show a couple of examples of that. So here's an example from cosmology. So this is the flagship run from the Flamingo project. It's 2.8 gigaparsecs, which is a stupidly long length. And we're seeing the cosmic web of the universe here. So galaxies live in this sort of sub-pixel scale map. And if you're interested in the matter clustering of the universe, for example, and maybe you want to work with all of this and measure kind of the separations between structures in this sort of large scale map. But you might also do galaxy cluster cosmology, and then you want to pull out one cluster which lives kind of in this scale. And if you work it out, this is actually not a two-dimensional thing, it's in a three-dimensional box. It's like 1/10 millionth of the box. Okay, that's a bit of a headache. Another example on smaller galaxy scales. So this is a different simulation, much higher resolution, much smaller volume. And so this is kind of the wide scale view of this simulation. This is actually about the same size physically as this box, but now simulated just that piece in a lot more detail. And then we can start to zoom in, right? So this blob conforms to this circle. And if we zoom in some more, it's on the very center here, there's a whole galaxy down inside here, right? And this galaxy is resolved with something like 10,000 particles, which is again about 1/10 millionth of everything going on in here, right? And again, you might be interested in pulling out just this thing, or you might want to work with the whole thing. Okay. All right, so to unpack this a bit more, here's hearing about Swift a lot all day. So here's kind of an example of the tools that get changed together into actually doing something with this code. Right, so it looks like spaghetti, but I'll walk you through this. So the key here, right, things in green are files and things in red are bits of software. Right, so we start with a bit of software to create initial conditions, and this is going to create a file of conditions. This is what we're going to simulate. So we have some initial state for our system. This gets fed into some simulation engine. For example, this could be Swift that we've heard a lot about with some galaxy information model implemented in it. That's going to run on a cluster for a while. And it's going to produce snapshots. It's going to dump to the state of the physical system every once in a while. And then we get a collection of what, in this case, some slice of the universe looked at different times. Right, and then this plugs into this box labeled post-processing. So once all this heavy lifting is complete, I guess we got raw outputs, and we'd like to organize and catalog this a bit. So one thing that happens in the structure finder, this goes through the snapshots and looks for clumps of particles that correspond to galaxies. So it groups particles together logically to these belong to one galaxy, these belong to a different one. And that writes out some kind of membership file that's just lists of particles with these IDs belong to these groups. And that gets logically connected together to snapshot the membership information. And then from that, we might want to produce sort of summary catalogs. That goes into this case code called SOAP. And that's going to, for each group of particles, calculate some summary statistics. So I might want to know for galaxy number 1, what is that galaxy's mass? What is its luminosity? What is its morphology? And just sort of summary one number of statistics for that galaxy. And that gets stored in a galaxy catalog. And finally, we do some analysis on this. So if I'm an analyst, I live in this space, right? I'm going to use the codes I'm going to talk about today, Swift.io, which can plug into either the galaxy catalog or into the snapshot files. And it'll read those and do some data visualization. And as a user, I might sit here if I'm just working on this, or I might sit here if I just want to work with the catalogs. Or I might chain those two together through another tool because I want to work with both in tandem. And then I sit down. Simple way. Okay, so I'll just kind of pull out a couple of example things that we have to worry about when writing these analysis codes. So I'm starting with Swift.io, which is slightly lower level, right? Interfaces directly with these data files. And yeah, so talk about some of the things that make these tick. So one of the crucial things is this selective data loading. So I showed examples that said I have this huge data set. I might just want one piece of it, or I might want the whole thing. So if you just want one piece of it, this relies on the data are stored in a specific way. So with this spatial domain, it's a large cube, and that's chopped up into subcubes. And then particles that belong to each of those subcubes are stored together, and then that's indexed in some metadata table. So if I want this subcube, then there's a lookup table that says, okay, that's stored on disk in this location, and go read just that directly. And so that relies on the data files having this spatial structure, and we have to have metadata files to go and read it. And so this diagram is just meant to illustrate that if I pick out some objects of interest, right, I'm interested in these little circled galaxies, then I'll be able to go and do my analysis. If these are the only galaxies I want to analyze, then I can get away with just reading these two subcubes. This galaxy, and maybe throw away the bits that I don't need. Log it one. And I never have to read any of these black cells, and so I've saved a lot of I/O. This is great, but it has some limitations. It does rely on my workflow being based on spatial selection. So if I had some science question that was like, give me only the hot gas. Well, the hot gas lives everywhere, but it's all mixed together with the cold gas. And so now I'm stuck, right? I'm going to have to read basically everything. And it's hard to solve that problem serving both this and every other possible use case of things. Also relies on my regions being made up of, well, either being cubic or kind of cuboid-ish, so I can chain together cubes to select them. If you say, I just want to give me every particle that's close enough to a diagonal line through the box, it's going to work. I'll kind of pick out the cubes close to it, but it's still going to be relatively inefficient. So, fine. Okay, this is the slide where I stop talking.
Would you please go on?
Okay, so when I started out working with these kinds of simulations back as a master's student, this was starting to happen a little bit, but the first tools that I worked with were built as, okay, you have a simulation data file, load the file, we're going to read the whole thing into memory, right? However big it is, whole thing goes into memory, go make a cup of tea, come back, and then we can do some analysis. More modern approach, lazy loading. So the data file contains many tables. If I don't need all the tables, don't load them all. Only load what I need when I need it. And okay, SwiftSimIO implements this. Struggled a bit for what to say about this feature because it kind of seems very obvious in hindsight, like why would you do this? But super important, right? I've tried it without lazy loading, and it was a much more miserable experience. Okay, yeah, on lazy loading. Another nice thing about SwiftSimIO is it mentioned metadata already. The Swift outputs are very nice. They have a lot of metadata. So the data describes its own physical units. You have these lookup tables of where to find ranges of particles within the file. You have all the data about how the run was configured. So like your code parameters. You have parameters describing the cosmology. There's lots in there. And it turns out you can have too much metadata. We found this. So came to realize at some point ran a profiler. This is from an old version of SwiftSimIO, and what we discovered is the metadata access is too slow. Right? So here's, I haven't seen these before. I know the text is tiny. I'll walk you through the important bits. Right? So this is some function call to open up a data file that we're going to try and use for some analysis. That took 25 seconds. And then this is split into different bits. And the important parts are, here's, okay, Python imports are slow. This is a separate conversation. Our actual data read for this is the bulk of the data in megabytes, 8 seconds, whatever that means. So a smallish file. And our metadata read 10 seconds. We spent more time working out like what data was available and where it was stored and all that than actually getting the data out, which is not great. And so one way to look at this is that we're victims of our own success, and the solution is simple, right? Data access is too fast, we just need to make this slower. No. Solution is actually lazy load the metadata too. So once you have enough metadata, turns out that can be your bottleneck, which is a weird place to be. But then this was a very easy win. A couple of lines of code later, our metadata read is a different cache file, a bit longer, 26 seconds down to 0.1 seconds, which is much more reasonable. And actually, we will spend this time in the end if you do decide to read every field in the entire file. It's just that this will then become a small overhead on data reads. So, you know, it'll always be like 0.1% of your total read time, which seems okay. I mentioned one other feature here. This is a new thing that comes out of some effort by John Helly, who's another local here. Turns out a lot more people have a laptop than have a compute cluster. And so this is in an effort to make the data that comes out of these simulations more accessible. There's some analysis workflows where you really do just need to load many gigabytes all at once and run some HPC code on it. Fine. There are other workflows where you do want to pull out just one tiny piece, and then that's easy to analyze on a laptop. Currently, the data does all live on some compute cluster, and so you either have to get an account or download these large data files. What John has implemented is basically an interface to HDF5 that runs over the network. So it feels just like Python. It feels just like H55, except that instead of giving a local file, you can assign a network server specification. File lives on the server, and now you're interacting with it just as if it's local, with the exception that anything we query from the file now comes as a download. So as long as you have a fast enough connection, works pretty well. The hope is that that will help open up the data sets to more people. Spend just a couple of minutes talking about this Swift Galaxy thing. So this is something very close to my heart. I wrote what eventually became this during my PhD, just to solve my day-to-day problems, and then realized that this was a fairly general thing. So it's a complete rewrite of my old messy student code. But the problem it solves is something like this, right? So if you want to work on one object from one of the simulations, first we load up the galaxy catalog, figure out, oh, this galaxy looks interesting, right? I've found that it has a certain mass and luminosity of whatever. That's the one I want. Now I go and read all the membership information, select down for the membership for the object that I want, load the particles that belong to that thing, probably recenter on that object, maybe rotate my coordinate frame, do some additional selections to just get subset particles I'm interested in. Maybe look up more properties from the galaxy catalog of this object that I'm interested in. Apparently I did twice, and then go and do some analysis. And the whole purpose of Swift Galaxy is, oh, right. This gets even worse if I've done this once and now I want to do it over and over again for many objects that I'm interested in. This can get very inefficient. And so the job of Swift Galaxy is basically to sit here. So we load up the catalog, decide what object I'm interested in, and then should be as simple as saying, here's my data file, here's my catalog file, here's the object I'm interested in. Now I can do analysis and live a happy life. And yeah, this is the last thing I want to show. And so most of this is just sort of relatively simple quality of life stuff, but where it really comes into its own is going back to this diagram before, where I have several objects of interest. There's, I think, a really fun optimization problem that starts to crop up. So this situation is pretty easy, right? I've got my circle of objects of interest. They all live in kind of independent groups of cells. And so I could just loop over these objects, and dependently for this one, I need to do a bit of I/O. I like to do a bit of I/O. I can farm these out into different processes if I want. Pretty easy. Where this starts to get interesting is if I add a couple more objects of interest. I have two down here. And the question becomes, okay, well, for this object, I need to read this cell. And for this object, I need to read these two cells. This one, I also need to read these two cells. So if I read all, actually, this one then changes to this. So should I read all these together and then just loop over the objects that live in these cells? And then, okay, well, the rest of them I can still treat independently. This isn't so bad. If you keep adding these, you find that eventually you just chain the entire box together. You end up in the situation of, well, I may as well just read everything. And that is one of the possible optimal solutions, right? Is just read all the data once and you're done. Turns out the other optimal solution is chop it up into chunks and read it all exactly twice. Read a little bit, work on it, discard it, read another bit, work on it, discard it. And because you have these overlapping tiles, you can't iterate once, you have to iterate, in a worst case scenario, twice. If you end up reading more than twice, it's not optimal. And so built into here, it's like this optimal iteration strategy where you will never read more than twice, or once if you're willing to do just hold all the gigabytes all at once. So lots of other things I haven't talked about in this talk, right? Your data are probably stored compressed. Compressed data means you can only read discrete chunks at a time. How you size those, especially in conjunction with the kind of spatial index chunks, is a very interesting optimization problem. Data integrity and redundancy, so backups, how do you manage your backups? I mentioned before, we tend to just analyze things the way that they were written out by the simulation. I think this is largely because we're too scared to rewrite in a new format, so we have no idea how to check that it's correct. Yeah, balancing performance of the sort of analysis code and user skills. So I think, well, this is all written in Python, which is an interesting choice if you care about performance, but that is what the users want. I've seen this go as far as had a code that had some C extension that had to be compiled, and the user said to me, well, I don't have a C compiler, so it seems as if I don't really want to get one. Okay. Yeah, parallel IO is a whole thing. Relational databases have an interesting role to play here, something that we probably underuse in this community. So yeah, happy to chat with people about any of these things. Propped up here, just summarizing. So this is, I think, inevitably an ongoing process. There will always be a new use case for the data that doesn't quite fit into the mold of the current data layout or tooling. And it's kind of an end-to-end thing, right? How the data are produced comes into it, how they're stored, and how the tools are written all comes together. And yeah, there's lots of tensions in the optimization between these very different use cases. Thanks.
Been mulling this over while you've been talking, but how much compute is wasted by people reading this data inefficiently that we could just run a conversion and store 2 times the data? There's got to be an answer to that.
It's a huge amount. So we discovered an issue. This is involving the compression. So simulations store things like we heard about chemistry. So it stores tables of the chemical abundances of different elements. And those were stored in like a 10 elements by a billion particles array. And that was compressed. And the compression was run such that to uncompress, you have to read a 10 by, say, a million, and then you can read another 10 by a million. And so those chunks have to come together because otherwise you can't decompress. And because of the 10 wide, this means you can never read one element. And it turned out the tools were actually written, so you could only ever read one element at a time. So you'd say, give me hydrogen. And it would go read the entire table, decompress, and give you hydrogen. And you say, now give me carbon. Go read the whole thing again. And so not only to get one element, you're reading an extra 9 columns. So you're, only 10% efficient. Now, if you want all 10, you have to do that 10 times. So you're 99% efficient. And so the solution is simple. You compress single columns. So we put that into Swift. That took an hour. Except for legacy data that already exists. There you have to rewrite the outputs, which is not a 1 hour job. It's a very long job, so there are many petabytes. It's not that big a deal, right? There's this thing called H5 repack. Press go and you wait. But you're scared you're going to corrupt something. Do you have backups on tape? And it's been sitting there for months, and so everyone is 99% less of, or wasting 99% of the, So don't do chemistry as the
I might have a question or two. So regarding the cubing approach that you have shown, any thoughts of say optimal cube size?
like this.
Should I be aiming for number of particles per cube, or should I be aiming for a certain chunk of the total data?
So there are many possible ways to balance that optimization, right? There's no, I think, global correct answer that I am aware of. This plays into the compression. So if your cells contain a lot less particles than are in one block of compressed data, then I don't know what I just said, but yeah, basically, if you're reading multiple cells in one compressed chunk, then that's basically wasted. And there is a sort of minimum size to that compression chunk, because if you make it too small, then you're uncompressing like a little bit and then uncompressing a little bit, and it runs faster if you have bigger pieces. So that's kind of a lower limit. There's some argument, so I think Josh Borrow has been talking about, what if you just went all the way down and just made this an octree that reverses all the way to the particle level? So that's means you need to sort before you write. It's already sorted. It's sorted into, well, it's sorted in the tree.
It's in octree order, yeah, I was literally
Right,
just
okay.
thinking this as you're talking.
Um,
We should write at the lower level. And and you could do it non-destructively by adding it to the snapshots as an extra cell group. And then you don't destroy it.
yeah.
This is an internal conversation. But, yeah.
So that's something else to think about. Eventually you get diminishing returns because of the compression. If you switch off compression at the cost of a factor of 2 in disk space or something, then you could make a lot of use of that.
In a very similar sense, if I may. So usually I'm more on the, let's say, user side of things. So I just get whatever cluster I had, and I just write data on there. So maybe you as a tool developer know a bit more about it. I would wonder, like, any of these strategies you've been showing, how strongly they would depend or could depend on hardware, the file system.
Sorry.
You need to go.
Short answer, quite a lot. So I don't think we make enough use of this, probably because this is all written in Python, because that's what people want. It's relatively hard to do that level of optimization in Python, but definitely notice like file system level things. There's clearly the disks are caching something somewhere, because if you read the same file twice, it works a lot faster the second time. Yeah, the parallel IO, I think, is something that we've come back to many, many times. Is that I mean, obviously this needs to happen, but how to make this portable across different file systems has never been clear to us, because like parallel IO on a Lustre file system compared to more generic file system or different kinds of RAIDs. No one's ever sat down and given that enough thought, I think, on this side of things. Clearly the outputs get written awfully fast because it's parallel, right?
Okay, so let us get Kyle again.
Oh, it's visible. Hello, everyone. My name is Dmitry Nikolaenko, and I'm a research software engineer from Advanced Research Computing at Durham University. And here I've been working on improving load balancing for the software called Piano. Here a little introduction. So Piano is the software, the framework to work with meshes, meshes which store data on cells, on vertices, on edges, for numerical simulations and modeling. And it has several levels of discretization. So level 0 represents the whole domain. Level 1 represents the next level of the discretization, and so on. And Piano so as I said, Piano is an adaptive grid framework. Underneath several tools, such as Hide, Swift. So for working with these partial differential equations, with particle simulations, it has lots of modules which support the work of Piano. It supports valorization, MPI, multi-threading, through space-tree-based domain decomposition, and all those data, all those information about the mesh grid is stored in. So the ordering is done through so-called Piano space curve, space filling curve. And then, and so load balancing strategies plug into this software because due to when you do massive simulations on multiple levels of discretization, you naturally are interested in parallelizing on a SIP computer, but it's not simple to do it in such a way that it's running with high performance computing in mind. So how load balancing works in Piano? So strategies are decision layers which tells Piano how to do splitting the trees. So trees are the way how information about the mesh is stored. It's organized through tree in space tree sets. And the core job is to trigger space tree split recommendations at the right time. So Piano provides a toolbox to do splitting. It does mesh traversals and periodically invokes the load balancing strategy. And then it realizes splits at the right moments and sometimes joins. This infrastructure serves both MPI and multi-threading. So basically, first there is the initial tree stored, let's say, on rank 8. All information on rank 8. And at some point, when the decision is suggested, oh, we need to split the tree, so then the second rank comes into the play. And there are several steps when certain data needs to be transferred to this second process. So let's look at the problem a little bit different. So this is the figure shows the multiple levels of the mesh. So it starts from, I don't show the level 0, level 1. Each cells on each level, they can, during the discretization, they can become parents or children. And so the splitting in Piano is done either in 2D or 3D. So 3 times on each side. So each parent could have 9 or 27 nodes, depending on the dimension. And then when discretization is done, so discretization is done in certain locations where it's really needed. So it's not necessarily the whole tree is discretized. So, for example, somewhere happens a turbulence where you need really tiny time steps or spatial steps. So that's where the discretization happens. So online and offline. So Piano Toolbox provides splitting for online, which on each grid level, it decides, it applies some strategy, and it decides, oh, here the tree needs to be split. What does it mean, the tree split? It means that now this parent node becomes the root of a subtree, which belongs now to another MPI rank or another process. So that each process now has only each portion, only its own subtree. But it carries with itself some negative things, such as that when we go down the grid, we cannot know how many cells will be in the subtrees. So, okay, we can kind of assume, have some guesses, but eventually the splitting of the whole tree into subtrees might become not efficient. And that's why we use offline. And offline means that we build the whole mesh with all levels at first. We build without balancing, and then we save it, just or we say checkpoint and analyze. And we've developed an API based on Python for offline load balancing analysis. And using that tool, we can derive a better split plan. So then we have knowledge about the whole tree, the whole mesh, and now we see, there are some leaf nodes. So we split first only leaf nodes. And by the way, all the key information for numerical simulations or data is stored on leaves. So because that's where we kind of are interested in most detailed simulation. And then as we got the split plan, at the stage 3, we got split recommendation. And now we are ready to restart again our simulation with a hard-coded airplane, which means we use these splitting instructions to insert into the restart of simulation, so to say. And thanks to offline load balancing, we can now focus on lowest bit cost. We can see, that's where we can do splitting better, so that all MPI ranks or processes are balanced with them. So during this split instructions extraction, we get subtree IDs. So we get how many leaves, how many leaf nodes should go to which subtree. But there might be, for example, 8 subtrees, but only 4 in the average. So there's needed also mapping from subtree IDs to destination ranks. Now, when this splitting is, when we analyze the mesh, how to better split, the algorithm should first of all, it doesn't repetition by itself, but it issues a split recommendation. And so Piano then itself it takes the final decision to how to split. Then Piano enforces certain constraints with regard to topology and regularity constraints. And then the composition is triggered. So space in growth, it is the way how all the nodes or cells of the mesh are ordered. So if you remember, you see a set of several meshes or different levels. And so on each level, all the nodes and cells are ordered in SXC order. But then there can be more domain decomposition, more levels, and so eventually some lead nodes go to one subtree, other nodes go to 7 sub 3 and so on. Yeah. All right, so now a little bit faster. So we have our architecture, the following architecture. Load balancing API consists of 4 phases. First phase is input generation. Either we read saved meshes, or we can also generate synthetic trees to analyze to analyze. And then the phase 2 is splitting strategy itself, and phase 3 is extracting harmful parameter, and phase 4 output and visualization. And we get from phase 3 necessary parameters for splitting, which then pass to backward strategy. All right, so inputs, that's not the most important thing. I'll skip. Now, stage 1 is a different distribution. So each next level means more detailed level of 23. So we have first we need to split all the nodes and as much equally as possible. So on this picture we see 6 go to the sub 30 and 5 go to sub 1. That's the stage 1, leaf distribution. Stage number 2, it's about bottom-up propagation. So it's more efficient to do splitting higher, because higher redistribute data less than. So if we are here on level 1, then we just distribute that little amount of data, and all the next data is automatically on the other So that's propagation up as much as possible. And then hierarchy optimization, because with that small tree is not possible, I'm showing on a bigger tree. So if we see here, we have still yellow sub 0, and the hierarchy optimization level discovers, here is better to have sub 3 to combine with this particular sub 3. From here also combining with this sub 3. So this result of splitting is more load balanced. And then the stage 4 is just about getting all that data. It's an example of Python code, which you would use to get these parameters which are needed to set a pathway to set for warm restart. Okay, and that's what is generated from the previous Python script automatically. It goes in C++. So it allows warm restart. And then all development is supported by unit testing and integration testing. So we make sure that everything works as expected. Then we have also visualization. So we have a demo which allows to run and see what happens, and it shows all splitting in real time, so to say. It shows the initial splitting, and also it shows the resulting splitting. Here you see the resulting splitting. And then we also are developing a tutorial which allows people to practice coding while using load balancing API. And sorry. Yeah, so that's my last slide. So the main outcome is that offline processing indeed improves the composition quality, and workflow is reproducible and test-backed. And the next step would be to apply the process to your own mesh snapshot. Thank you.
Okay, we're running a little bit over time. Any questions? Ooh. Lucky me, I get to. So about the offline processing, I'm not entirely sure I understood the entire concept as opposed to online. Because you wrote on the side, it's online doesn't have access to future tree decompositions.
So online doesn't have information about future mesh, and that's why. So it lacks certain information, and I believe that it also may be due to dynamic load balancing, because you need to sometimes, like if you simulate flows and some places are moving around, so you need these different levels of grid mesh in different places all the time, and that's something which you cannot predict. That's my understanding. And with offline, you basically by building the mesh, you know now all the information, and then you save it, and then you kind of separately, with using the API written in Python, you analyze how to better split, and that's hard coded. That's a kind of type of strategy. Piano has other kind of other offline strategies which you can, or online strategies which you can apply, but it's can be not efficient always.
But see, that's a little bit the bit that confuses me, because in order to have all the information, you kind of need to complete the run, and then I'm done.
No, you build the mesh, but you don't run the mesh. So you get the information about the mesh at this point. You start the simulation, and you kind of okay, you calculate what mesh should be, or it's given in some way. But then okay, you can start running, but okay, initially it's just on the whole information is on one process, so you need to split it. Okay, you might want to use an online approach, then it splits, but then you run and it turns out, oh, it was not efficient. So it would be better if you use offline, because yeah, you need to, in order to analyze how to better split, you need to save that mesh. That's why maybe it's called also offline. So you read that mesh and then you do analysis.
So you do analysis on previous meshes, not on future ones.
On the current mesh, as I understand. So, and then okay, I guess you get the best splitting right now, and you do simulation, and then after maybe periodically it does remeshing, so the mesh changes, and then you need again to adapt. So theoretically, you need to do load rebalancing again.
All right, thank you. Are there any other questions? No. Okay, then let us thank Dimitri again. I will conclude with just a few words. It's been a pleasure to host this HPC and Astrophysics session. I hope you enjoyed it as much as I did. This is the end for today. In terms of sessions, there should be dinner. If you're lucky, the beer is already on. So yeah, I'll see you over in the Manchester. Thank you all.
Thank you, guys.